Okay. Good morning, all. Thank you. I apologize. Due to work commitments, I haven't had enough time to prepare this as much as I should have. So I looked at the presentation a few times, but you probably will see that I stutter through it because I'm not fully up to speed with the presentation as it stands. So a lot of it has been discussed by Josh. Parts of Luke's presentation as well were part of my initial studies for my research. So in the presentation, I'm going to look a bit at the background and aims, not arms, of the project. I'm going to describe a bit the study, look at the results, and take some conclusions that will probably be very similar to what Josh has seen in his study. So race cars are generally designed in wind tunnels, which are generally undisturbed flows with very low turbulence intensities, which really allows for very consistent and repeatable results. The problem is the car is optimized to work under those conditions. When you reach a track, you actually have other cars on the track, you have wind, you have different parameters. You might even have thermal boundary layers close to the ground. So different things happen on the track that aren't easy to replicate in the wind tunnel. So the aim of the project, although initially it started as something similar to what Josh was doing, but due to the complexity of it, the idea became to identify the main flow structures that are generated by a leading car. So change of local flow incidence. If you have a wing in the wake, the flow incidence will change span-wise. There's a reduction in the dynamic pressure, and there's quite high turbulence intensity in the wake. Now, next bit was to determine how those wake characters influenced the front wing of a trailing car, and understand the changes that happen both on the surface and off the surface of the wing. So, just like Luke, I used the DS Houghton wind tunnel. The only difference between my experiment and that described by Luke previously is that my free stream turbulence was slightly higher. Because I was going to use a laser Doppler anemometer, I had to put a flow seeder inside the tunnel itself. So that, although there are turbulence reduction screens in the tunnel, it did increase slightly the turbulence in the test section by about 0.4%, totaling 0.7. But the boundary layer thickness remained unchanged. So, although I had access to an actual Formula One wing that was tested at the beginning, we thought that it was more of an industrial project than an academic project. So we decided to go for a slightly simpler wing, a wing that had been studied before, and sort of did a 50-50, so 50% academic, 50% F1 wing. So the dimensions of the wing would fit within the regulation box of the F1 technical regulations in 2009. The only difference is I do not have the symmetric Y250 section in the middle. So the wing has a GAW1 airfoil section, which is just the airfoil the section extruded for the full span of the wing, and it has two Reynard-Kiley flaps that, although I'm only presenting the results for 23.9 degrees, I had the option of 3 different degrees, so 13.9, 23.9, and 33.9. The other option I also had was to change end plate configuration. So there was quite a bit of scope for understanding the influence of the leading car on the trailing wing. The balance, the force balance, was inside that streamlined body, and all the forces were just measured off the wing, so no forces from the body were actually recorded. Based on a design done at Durham University previously, although I did not have the dimensions, I roughly estimated how big it would be, and I tried to follow the rear wing and diffuser regulation box from the 2009 Formula One technical regulations. Hence, my wing, in the end, is slightly higher than Joshua's wing, which will lead to a slight difference in the results I'll be presenting further down. The only issue was I wanted to study a car separation of 0.5, so it would be 50% of a car length. But that would mean that my wake generating model would have to be on fixed ground. So it isn't on the rolling ground, it's positioned on top of the boundary layer suction box, which was turned off. It ended up being that with the boundary layer suction box turned off, the results were more representative than with the boundary layer suction box on, as it altered the flow from the diffuser. So accuracy of the model, so the positioning of the wing was done by 4 pins on the end of the wing, and the height was measured to the ground. The chord-wise Reynolds number is representative of 25 meters per second. Data was acquired at 10 hertz for 20 seconds at each point. I did 22 write heights. We did try different logging frequencies, but in the end we found out that 10 hertz did not make a significant difference, especially in the undisturbed cases. In the disturbed cases, there was a slight offset, but about 95% of the runs were repeatable. No force data was taken into account for any deviation, and the uncertainties were calculated based on the different parameters that you could set up. So wind speed, positioning of the wing, height, incidence angle, all the parameters that would influence it. I also did some flow-viz that was later used, was later used to validate the CFD approach that was carried out. So using the LDA model, using the LDA to do a wake survey, I measured planes downstream of the wake generating body to understand how the wake is developed and how the trailing wing sees the wake. So I measured a plane, so this is taken from CFD, but this first plane is at a quarter car length distance, and the second plane is at half car length distance. I also took some longitudinal planes, one that's lined up with the center section of the wing, one that's lined up with the tip of the wing, and another one that's halfway in between, so we can understand the differences in the flow at these 3 points. So the computational method came up because we had some equipment that broke down, and because I was a bit stuck, I decided to use the LDA data that I had acquired to validate a computational method. So a domain was generated that was 3 times the length of the wake generator upstream, 7 downstream, and it had roughly a blockage ratio of 3.5%. The wake generator on its own was 34 million elements, and I used the same domain to immerse the wing, because the wing is much smaller, the domain actually fit inside, and that took us to about 52 million elements. I was using the KKL omega turbulence model because I wanted to fully resolve the boundary layer of the wing, so I could compare with the flow-viz results that I had seen. The initial results I had obtained, which were then used by Luke, I found a bubble, and I wanted to understand what the bubble was doing. So I actually needed to have the proper boundary layer on the wing to validate everything. So in Fluent, I ended up doing the exact wind tunnel. So there was a stationary part for the wake generator, and there was a moving ground for the wing. And it took about 6,500 iterations to fully do the calculations, but I just left it running for an hour longer just to be certain that it had converged. So on the left-hand side, we have the wake generator results measured with the LDA. So one interesting bit that we noticed immediately was the rear wing of our wake generator was actually partially stalled, which wasn't perfect, but we were running out of time, or I was running out of time, so we carried on with the work. In the middle, so this left-hand side image shows us the normalized longitudinal flow speed. So as we can see, there's a big deficit at about halfway down between both cars. So there's this very low energy area. And just by looking at it, we probably can understand that there might be some upwash. Going into CFD and running the same model in it, we found the results matched almost perfectly. And when I did a validation of the wing on its own, the boundary layer, and everything, just the forces on the wing, and the boundary layer matched within about 1% of the actual location on the experiment, and the forces were 0.1% off, both lift and drag. So comparing both CFD and LDA, I had a very good correlation between one and the other, although turbulence intensity is slightly lower on CFD. But carrying on, looking at the vortex structures in the image on the left-hand side, I identified two different vortices, the main stronger one coming from the rear wing and a slightly smaller one coming from the diffuser at a quarter car's length separation. This shows up and doesn't show up in Joshua's work because my wing was further away from the diffuser. So, but when we move downstream, both vortices end up merging and we only have a pair of counter-rotating vortices. So validating the LDA with the CFD, although the velocity profiles do not match up perfectly, the trends are there. The forces match up perfectly, the flow on the wing matches up perfectly, but the wake itself does not match up perfectly, but I was stuck with it. So on the left-hand side, we have the longitudinal velocities. On the left-hand side, we have the vertical velocity component. On the top, we have the center line of the wing, in the middle, the midspan, and the wingtip. So one thing that is noticed is there's a significant velocity deficit in the longitudinal direction in the center plane, and there's quite a bit of upwash. But once we move towards the wingtip, the velocity deficit is slightly smaller, but we get downwash. So we get effectively different loading depending on where the wing is. So in the middle, when we have upwash, we're reducing the angle of attack, while at the tip, we're actually increasing the angle of attack of the wing. Now, you can see this in IndyCar quite well. When two drivers are behind each other, the trailing car tends to move to offset itself slightly to use the downwash from its rear wing to gain some front downforce. So the experimental results, similar to the previous presentation, there's a reduction in downforce in CL, and there's a reduction in drag. The quantities are, although CL is very similar, I get 42% reduction in drag. In downforce, the drag also falls by about 40%. But in the end, we're comparing a front wing in isolation while Joshua was comparing a complete car. But the trends are still there. The operating window of the wing, or the operating range of the wing, is where the wing loses most of its performance. So going back to the question that was raised before, there's not really much that can be done. So the flow visualization, one of the things that I had right at the beginning was the laminar separation bubble in the undisturbed flow. So we can see that there's a laminar region, a separation region, and a turbulent region. While in the disturbed flow, due to the turbulence intensity of the flow is fully turbulent throughout the chord of the wing, so no laminar separation present at all. If we compare the undisturbed with the disturbed results, we see that the wing in the center section actually is where you lose most of its downforce. But if we go back to the results, we see there's upwash in the middle, angle of attack is smaller, so a lot less downforce, which is expected. We also see a significant change of pressure distribution on the underside of the body that has the force balance inside. This alters the pressure recovery of the front wing, and leads to a change of effective flow angle coming off the wing, which leads to the separation noted at the trailing edge of the main plane. The other thing that is noticed is, because we're producing less downforce, wingtip vortices are weaker, although the tip vortices of the wing are slightly less affected than the tip vortices of the flap. So, concluding, as shown in previous studies, there is effectively a reduction in dynamic pressure. There's varying local flow angle incidences, and there's high turbulence. It is possible to replicate a complete car in the tunnel with a short bluff body. The only problem is it's shorter, it produces less downforce, so the major flow features of the wake won't be as intense as on an actual car body. The three different phenomena that lead to the changes in the wing operation cause the shift in the stagnation points of the wing. It reduces the suction, and the downforce generation by vortex suction also disappears due to the vortices being weaker. The wake is generated is basically formed by the two counter-rotating vortices as mentioned before, and these cause the upwash at the central section of the wing and the downwash at the tip. So, designing a car to operate in a wake is very difficult. You are always going to get loss of downforce and drag, and it's very difficult to actually design it because each car has its own wake. So in the end, you can't really do anything about it. And especially in the operating range of the wing is where you actually have the biggest losses. So there isn't really a clear answer on how do we change the regulations to make cars work close to each other. So other conclusions, I've already run out of time, I'm sorry. The high turbulence causes changes to the flow on the surface, so the bubble disappears. As I've just mentioned, it's unfeasible to design the car especially operating in a disturbed flow. You could try to design it to run at ovals, for example, just to make a pole or something. And the dynamic pressure loss means that the wing, independently of its geometry, will always lose downforce and drag. So, as I've lost out of time, this is the last slide. Thank you for your attention.